is flying by on this busy, crowded planet. As life changes and evolves from second to second. And yet the arc of human lifespan is getting longer. 65 years is the global average, way up from just 20 in the Stone Age. Modern science, however, provides a humbling perspective. Our lives, indeed the lifespan of the human species, is just a blip compared to the age of the universe, at 13.7 billion years and counting. It now seems that our entire universe is living on borrowed time, and that even it may be just a blip within the grand sweep of deep time. Scholars debate whether time is a property of the universe or a human invention. What's certain is that we use the ticking of all kinds of clocks, from the decay of radioactive elements to the oscillation of light beams, to chart and measure a changing universe, to understand how it works and what drives it. Our own major reference for the passage of time is the 24-hour day, the time it takes the Earth to rotate once. Well, it's actually 23 hours, 56 minutes, and 4.1 seconds, approximately, if you're judging by the stars, not the sun. Earth acquired its spin during its birth, from the bombardment of rocks and dust that formed it. But it's gradually losing that rotation to drag from the moon's gravity. That's why, in the time of the dinosaurs, a year was 370 days. And why we have to add a leap second to our clocks about every 18 months. In a few 100 million years, we'll gain a whole hour. The day-night cycle is so reliable that it has come to regulate our internal chemistry. The fading rays of the sun, picked up by the retinas in our eyes, set our so-called circadian rhythms in motion. That's when our brains begin to secrete melatonin, a hormone that tells our bodies to get ready for sleep. Long ago, this may have been an adaptation to keep us quiet and clear of nighttime predators. Finally, in the light of morning, the flow of melatonin stops. Our blood pressure spikes, body temperature and heart rate rise as we move out into the world. Over the days and years, we march to the beat of our biology. But with our minds, we have learned to follow time's trail out to longer and longer intervals. Philosophers have wondered, does time move like an arrow, with all the phenomena in nature pushing toward an inevitable end? Or perhaps it moves in cycles that endlessly repeat, and even perhaps restore what was there. We know from precise measurements that the Earth goes around the Sun once every 365.256366 days. As the Earth orbits, with each hemisphere tilting toward and away from its parent star, the seasons bring on cycles of life. Birth and reproduction, decay, and death. Only about 1/billionth of the Sun's actual energy hits the Earth, and much of that gets absorbed by dust and water vapor in the upper atmosphere. What does make it down to the surface sets many planetary cycles in motion. You can see it in the annual melting and refreezing of ice at the poles, the ebb and flow of heat in the tropical oceans, the seasonal cycles of chlorophyll production in plants on land and at sea, and in the biosphere at large. These cycles are embedded in still longer Earth cycles. Ocean currents, for example, are thought to make complete cycles ranging from 4 to around 16 centuries. Moving out in time as the Earth rotates on its axis, it completes a series of interlocking wobbles called Milankovitch cycles every 23 to 41,000 years. They have been blamed for the onset of ice ages about every 100,000 years. Then there's the carbon cycle. It begins with rainfall over the oceans and coastal waves that pull carbon dioxide into the sea. There it's captured by ocean plants, including tiny organisms called plankton. They are eaten by fish and other creatures, and the carbon is passed on up the food chain. Eventually, when plants and animals die or expel waste, the carbon falls to the ocean bottom, where it's impounded in layers of sediment. Without people, it takes a volcanic explosion or a dramatic lowering of sea levels to send the carbon back into the air, often after millions of years. The idea that Earth and life changes on deep timescales emerged in revolutions of thought associated with Copernicus and Darwin. But the processes that shape a planet like ours play only the smallest of roles in the evolution of the cosmos. So to glimpse time's broadest arcs, we must look to the universe beyond. The reigning theory is that it all began in a sudden expansion of space, the Big Bang. This was the time of the very tiny. The first microseconds set in motion the primordial era. Atoms formed within a hot soup of subatomic particles. The universe cooled as it ballooned outward, growing dim and falling into what's known as the cosmic dark ages. But gravity was always at work, particles pulling on one another. And after several 100 million years, considerable clumps of matter had drawn together. These isolated pockets of gas became dense enough to heat up and ignite. So began the era of stars. In this glorious age, the universe planted the rich cosmic landscapes we see in our telescopes, where hundreds of billions of stars light up galaxies all across the universe. The arc of this great era of stars is defined by the life cycles of those stars, which vary according to their sizes. Stars shine because gravity crushes matter into their cores. The energy released pushes outward and balances the inward force of gravity. This battle between energy and gravity is still raging in stars all around the universe. But in large stars, about 10 million years after their birth, gravity gains the edge and tips the balance. When the core of such a star crosses a critical mass threshold, it collapses in on itself. The energy released causes the star to explode in a blast of light and debris that's visible across the cosmos. In the wake of this supernova, shockwaves can cause nearby clouds of dust and gas to collapse and catch fire, to form a generation of smaller stars like our Sun. But when Sun-like stars go, their end will be more of a whimper than a bang, as shown in this gallery of dying stars captured by the Hubble Space Telescope. As their cores get heavier and heavier, over billions of years' time, fierce winds will begin to push on their outer layers, causing them to blossom out in spectacular displays. That's just what happened about 12,000 years ago to the star that's become the famed Helix Nebula. Today, we see the dying star's outer layers form a vast glowing ring. On the inside of the ring, spokes of more dense gas are being exposed by its winds. The star itself is now a dim, cooling remnant called a white dwarf. It's the size of the Earth, but about 3 million times more dense. This is likely what's in store for our Sun. A civilization distant in time may scan the Sun for planets, but they won't see Earth. Our home planet's end will have begun long before that, as rising solar luminosity gradually blasts away its atmosphere, rendering it uninhabitable. Surface water will disappear, evaporated by all that heat and stripped off by solar winds. Finally, as the Sun blows off its outer layers, they will envelop the Earth. Friction with those gases will cause this once blue world to gradually spiral home, melting into its mother Sun. This battle between energy and gravity repeats in every corner of a galaxy like ours, with gravity drawing gas clouds into stars. The stars will burn themselves out on a wide variety of timescales, depending mostly on how large they are. They'll leave remnants that grow slowly cooler. As a result, galaxies like ours will grow dimmer over time, unless they get seriously stirred up. That's what's going to happen to our galaxy. At just about the time our sun begins setting its sights on swallowing Earth, any remaining inhabitants here will see the stars of the Andromeda galaxy looming above the plane of our Milky Way. As shown in this simulation, the two are likely to tear each other apart, or at least severely jumble each other up. If it's a direct hit, all the stars in both galaxies will gradually join together in a gigantic galactic puffball known as an elliptical galaxy. All this turbulence of the merger could stimulate a wave of new stars being born, reinvigorating this new, larger galaxy. Dust-ups like this, where galactic neighbors come together, will be common as the epoch of stars grows toward its later stages. But a wholesale thinning out of the universe is inevitable on a grand scale. Recent studies of the cosmic expansion rate show that the universe is in no danger of succumbing to gravity. It won't all end in a big crunch. In fact, over the last 6 billion years, it's begun to accelerate outward, as gravity begins to lose its grip on the universe to an unseen force called dark energy. You can see evidence of this now, out in the huge voids of space between clusters of galaxies. Think of the voids as ever-expanding bubbles. Where the bubble walls touch are filaments of galaxies. As the bubbles grow, these filaments will stretch and break. The distances between galaxies will widen at a faster and faster pace. Eventually, most observers will see only a few isolated clusters of galaxies huddled together, with little connection to anything else, and few clues as to how they got there. A good place to be, in those long twilight years of the stellar era, would be a place where gravity and energy have forged an extended truce. Perhaps a place like this. It's one of the smallest and dimmest stars in our universe, and yet brown dwarfs have been shown to harbor planets close enough to bask in their dim rays. Brown dwarfs, and their hotter cousins, the red dwarfs, form the vast majority of stars in our galaxy. Because they burn so slowly, they will be the final beacons of the majestic age of stars, an era that will extend out to 100 trillion years. Even as galaxies like ours grow dim, another process will begin to transform them. Over time, chance encounters between objects will perturb their orbits, sending some towards the centers of those galaxies, and others flung out into the void. In this way, galaxies may gradually evaporate, with ever more dense concentrations of matter accumulating in their cores. The universe now begins to take on a new character. Welcome to the degenerate era, in which the cosmos is populated by red and white dwarf stars, steadily cooling, and by the charred remains of supernova explosions, the neutron stars, and black holes, slowly spinning down. Even though these dead stars have used up their nuclear fuels, the universe continues to produce small amounts of energy. They scoop up and annihilate dark matter particles that manage to stray into their grasp. Now here is where change slows to a crawl. It's expected that protons, the building blocks of all atoms, will slowly degrade, turning back into subatomic particles that then decay into photons, particles of light. All the protons in the universe date back to the earliest moments. Their decay marks the end of the degenerate era, around a billion years after it all began. That's a 1 followed by 40 zeros. Our picture of what happens after that will come to depend on what we learn in the next few years beneath the border of France and Switzerland, in one of the largest physics experiments ever undertaken. 100 meters underground, the Large Hadron Collider was built to accelerate particles in opposite directions through a ring of tubes 27 miles around. When they reach nearly the speed of light, scientists bring them into ferocious collisions. One goal: to define the final time horizons of our universe and the final moments of one of its most persistent objects. Black holes, ranging from millions to billions of times the mass of our Sun, occupy the centers of most large galaxies today. As those galaxies age, much of their mass will spiral toward the center. And over trillions of years, that mass will fall into ever more ravenous black holes. Conceivably, these ultramassive black holes could end up weighing as much as a galaxy. When they finally stop growing, will they too be subject to the ravages of time? According to the physicist Stephen Hawking, the answer is yes. He proposed a theoretical process of decay that scientists are hoping to test in high-energy particle collisions at the Large Hadron Collider. The idea is that throughout the universe, particles of opposite charges constantly well up in the vacuum of space. They normally destroy each other, but when this happens at the event horizon of a black hole, one particle can be pulled in, while the other escapes. That has the effect of slowly siphoning energy and mass from the hole. If this is true, then even black holes are eventually doomed. But finding out for sure is not easy. Creating a micro-black hole, it seems, will take more energy than any Earth-bound collider yet conceived can pack. That is, unless there's more to our universe and to gravity than we've thought. The key lies in whether the world we know is part of a more complex cosmic reality, beyond the 3 spatial dimensions plus time that we experience in our daily lives. If so, we would be like insects living on the 2-dimensional surface of a pond, completely unaware of the deep and complex reality below us. It may be possible that one of these extra dimensions could intersect our universe on an extremely tiny scale. According to some scientists, when particles collide at very high energies, the additional gravity needed to create a micro-black hole could come from this extra dimension. They'll know a black hole is there when they see the shower of particles predicted by Hawking's theory. That shower will open a brief window into a deeper cosmic reality, while shedding light on the ultimate future of our universe. Based on Hawking's theory, the last black holes will disappear when the cosmic clock strikes 10 to the 100th years from now. That's a number known as a googol. That's the end of our universe, and yet it's still far short of forever. What will happen, say, in 10 to the googol, a googolplex years? Well, if you wrote all those zeros out in tiny 1-point font, it would stretch beyond the diameter of the observable universe. Will the great arrow of time ever come to rest? Or does that arrow fly a curved path, destined to cycle back again and again, as whole new universes come into being in a way similar to our own? The numbers that describe the time horizons of our universe are incomprehensible, yet they may well be relatively insignificant in the grand scheme of things. Earth and humanity are products of the great era of stars, and we have been witness to its great spectacles of gravity and energy. Yet it's fair to say that we occupy a truly tiny period within the vast cosmic sweep of deep time. And we can easily imagine there are others out there, somewhere, who also look out and attempt to comprehend the changes they see. They too may invent the idea of time and develop their own theories on where it's all leading. Will their discoveries, and ours, somehow survive as we all gradually go the way of the stars that made life possible?